and how they are, how the structure of the microstructure is. Why we are using textile composites compared to the conventional laminated composites? Textile composites offer lightweight, high specific strength, high specific modulus, and superior fatigue properties. So the inspiration comes from a textile fabric. If you can see, it has a very high tensile strength, but it's very easy to bend. This is a common property of any slender structure. But this has a lot of applications because we want the material to bend but not fail. We want the material to undergo deformation but not fail or fracture. So this is the reason why textile composites have superior properties compared to laminated composites, but we have challenges. The first challenge is the design challenges. As Rajesh was talking in the earlier talk, the inverse problem of defining the structure of the textile composite microstructure based on the application is very difficult. Let's say you want a component to undergo some amount of loading, undergo some amount of deflection. Now let's go back. Let's try to define what kind of structure we need. Do we need braided? Do we need woven? Do we need knitted? What kind of fibers we are using? These are very difficult problems because there are a lot of parameters and there is no correlation between them to go from application to the microstructure. The second challenge is manufacturing. With the current manufacturing capabilities, the textile composite, the final part that you design, have poor torsion and shear properties. So this has a limited application of textile composites in the industry. And finally, we have numerical modeling challenges, which is like, how do we try to come up with a tool which can be used as a replacement for the experiments that we have? Like in the yesterday's talk also, we were saying that it's difficult to do experiments. Like our Airbus person was talking yesterday, that it's difficult to do experiments because it costs a lot of money. But numerical modeling is challenging because we can't accurately represent whatever is happening in the experiment. So currently what I am focusing on is the numerical modeling challenges, and I'm taking a woven composite microstructure as an example. Let's go with applications. The applications are first, I've looked into literature to just point out some applications of textile composites here. We have wearable electronics, which is gaining a lot of popularity in these days. And they have, in this work, they have used a graphene-based textile composite to come up with a wearable electronic device which can be used. And then the second is in the area of robotics. Here also they have used a textile composite. They have used a polymer-based textile composite, shape memory alloy-based textile composite to come up with a pick and drop kind of a robotic arm, you can say. Next, we talk about automotive applications. Here, they have used a textile composite based woven composite, 3D woven composite based bumper in a boat. They call it as a 3B. And then in the last literature, as Professor Chiara Bisagni was talking, they have used they've manufactured a stiffened panel using a textile composite here. So these are some applications. Now let's talk about the problems. This is the main part of the presentation, where now we have these are a lot of terms that you'll find in any general numerical analysis which you go through. Now we have to pick your poison. So we'll start with a small complexity and then improve the complexity as we go on. So the problem one is this. We are taking a 2D case, isotropic, small strains, small moderate strain, static loading, strain displacement, nonlinearity, slender beam with large displacements. Now we go ahead and see what these have on the implications, like what equations we will get because of these assumptions. So first is, we are taking a slender beam with 2D with small or moderate rotations. Now take from us general displacement and then assume that you don't have any cross-sectional warping, and then it's a 2D problem, so U2 is 0, and then you get the equations for displacement. Now we assume that we have large displacement and there is strain displacement nonlinearity, so we need to take a Lagrange strain tensor instead of a symmetrical tensor. Now we assume isotropic and no cross-sectional warping. So isotropic has the simple constitutive relation. Now we take static loading, because of which we get the variation statement where we don't consider dynamic loading or time discretization. Now we solve this problem. After this, all that is left is to discretize this, use FEM, write the code. So when we do that, we have assumptions made here. We take the displacement as linearly varying and the vertical displacements as cubically varying. The phi is the Hermite cubic function, psi is the linear Lagrange polynomials. Now, as Jay Raju yesterday was pointing out, the invalidation is very important for any FEM problem. So for every case, I've tried to validate this thing. So here, this is taken from literature. The validation case is a simply supported beam with UDL. These are the parameters, and this is the result. We expect the result to match exactly with the experimental values because this is a very simple case. And now let's move on to problem 2. Again, we go back to the set of terms which you'll find in any FEM or FEM paper or any literature based on numerical analysis. Now let's complicate things a little bit. We are changing it to 3D, and we are considering the rest of it remains the same, and we are considering large rotations. This will have a lot of implications, large rotations and 3D. So now the similar thing, we'll consider the position vector, and because of large rotations, we have the deflected. This is the undeformed position vector. This is the deformed position vector. And again, we are not considering any cross-sectional warping. So the D2 and D3 are the basis vectors, you can say, and it's rotated using a rotation tensor R. So now, based on the strain displacement nonlinearity and isotropic assumption, we have a 3D constitutive law of the same isotropic that I showed you in 1D, sigma is equal to into epsilon xx. We'll have a 3D constitutive law here. But since we are considering large strains and large displacement, we have to consider Green-Lagrange strain tensor and second Bialo-Kirchhoff stress tensor instead of our Cauchy stress and Cauchy stress and symmetric strain tensor or small strain tensor. So this is the strain energy. Now the problem comes because we are considering large rotations. The R is the rotations are no more additive; they are multiplicative, and this causes a lot of problems. Because while deriving the element stiffness matrix, we come across a lot of math which is difficult to understand, but eventually it boils down to a simple algebraic equation which we need to substitute in the FEM problem. So how do we simplify this? Instead of writing the code for 2D case, it was simpler to write the code, nonlinear FEM code, but for 3D case, this is much more complex. So that's where we go into automation of finite elements. Here, what we use is a combination of symbolic and algebraic computational systems and automatic differentiation tools to come up with a simpler approach to solve the same problem. So what is the symbolic and algebraic computational tools? To put it simply, it's Mathematica. But what Mathematica offers is you can derive the formulas. You can, for example, you can derive the formulas and generate numerical codes. But the problem with Mathematica is that we can use only one isolated formula. Let's say we have a loop, like in finite element, we have loops. We need to assemble the stiffness matrix. We need to solve a nonlinear FEM code using Newton-Raphson. This creates a lot of problem because there is uncontrollable growth of expressions. So this makes the code inefficient. So that's why people prefer using a Fortran, using a C++ rather than Mathematica or Python, because not Python is not in this way, but Python is also slower. But here in this case, Mathematica, there's a different reason why it's slower. So come automatic differentiation tools. What we do here, this is probably the bottom, the bedrock of machine learning, automatic differentiation and backpropagation algorithm. But here in the Corelk, if I'm pronouncing it right, he has used this innovative idea to develop a tool called as AceGen, where he uses the different ideas like automatic differentiation and symbolic and algebraic computational tools to simplify the process of developing code. So he calls it a simultaneous stochastic simplification of numerical code. Now, this results in the 3D geometrically exact beam element. Now, the general process of solving finite elements, before doing this, I'll just show you the flowchart. The general process of solving the finite elements is that you first initialize the primary variables, then you find out the element stiffness and force vector in case of a linear FEM, But in case of a nonlinear FEM, you need tangent stiffness and residual vector. And then you assemble them and then assign boundary conditions, solve the equation, check for convergence, go back. Now we are using ASGen. Here, the brown box is being covered by ASGen. So ASGen, you just have to input your this thing. Like I showed you here. You just have to input these formulas as it is. Like they have some particular syntax. You just have to input these formulas as it is. And you don't have to worry about how to assemble the stiffness matrix. There are a lot of complications that come there, which are not really related to the scientific reasoning. Like for example, in FEM, you assemble that the code is not converging. You don't know why it's converging, why it's not converging. You have to break your head to try to come up with the debugging process, which is very irritating and time consuming as well. So ASGen offers a simplification there. So using that, the simplification is also in the process of deriving the final algebraic equation. So as you see, if you remember, the simple process of FEM is that you have a variation statement, you minimize it, and then you discretize the equation and come up with the algebraic equation. If effectively what you're doing is you're minimizing the strain energy with respect to the primary variables, and the tangent stiffness matrix is nothing but minimization of residual with respect to the primary variables. So you input the syntax in this way, and ASGen helps you with calculating the element stiffness matrix. And that's not the what do you say? That's not the beam element that I have been explaining. It's an example problem that I've taken from ASGen where they have used a 3D element. I'm still working on the beam element part. So that's all. That's the second problem. Now we go back to our familiar terminology, and then we go with the problem 3. Now we are increasing the complexity again, including contact. Now we take the beam element that we have. Now we add contact boundary condition, which is a boundary nonlinearity. Now let's understand how to model contact in beams. So the first step is to search for places where there are contact. So essentially, this has been taken from the reference of Przemysław Litwiuka. He has written a book on contact between beams. If anyone's interested, it's kind of like a Bible for contact between beams. But if you want to go back to studying contact, Professor Peter Riggers is the most renowned name there. But let's go ahead now. So we have beams. Now we differentiate it, we discretize it, and then now we check for the closest elements within the different beams. So let's say this is first beam, this is second beam. Now we take the element, find the midpoint, and then find out which elements are closer. This is the global search. Now we go back, and this is the condition. This is called as the orthogonality condition. What this basically says is, if 2 points are very close to each other, the normal has to be orthogonal to the tangent between 2 beams. This is a simple condition. Now we have written this in the form of an equation. Often in a general case, what happens is this is a nonlinear equation and this has to be solved iteratively locally. Now, after finding out the places where there are contact, we have to impose a contact constraint, wherein we calculate the gap function. If gap function is less than 0, there is penetration, and then we have to include it in the calculation of nonlinear FEM. And if the gap function is greater than or equal to 0, they're separate bodies, and we can go ahead. So here, for a case of a simple circular beam, the gap function is the distance between the center lines minus the radius. If you're not considering any cross-sectional warping, this is the simplest approach. And then now we apply the constraint. Basically, this eventually leads to a Kuhn-Tucker condition, which is very famous in optimization literature. And now the simple thing is the pi is the energy of the beam. Now we add the contact part, which is being added as a penalty parameter. So there are 2 ways of solving an optimization problem, like 2 very popular ways, which are penalty and Lagrange multipliers. So Lagrange multipliers lead to additional variables, which can lead to, for example, if the stiffness matrix is there, we'll have a diagonal 0 element in the diagonal. This will cause complication while solving because that will lead to a singular, I'm not sure, it's not singular, but the 0 on the diagonal will lead to a different solver. We'll have to use a different solver or modify the stiffness matrix in such a way that we can use the solver. So zeros are being changed. This leads to complications. So people usually prefer penalty parameter. And then the steps are same. Now we take the variation statement. We'll find out the first variation, then linearize it to get this tangent stiffness. Now again, we use the same ASGen, and instead of doing all that, we just specify the how we are like calculating the first variation or first differentiation, minimizing the work to find the residual and the stiffness, tangent stiffness matrix. Now again, I have taken an example problem from ASGen where I have taken a 2D hyperelastic material, and I've taken a node to segment contact element, and then I've simulated the results. So yeah, so this is also I'm working on using beams to model the same. But currently, I've just tried to explain using an example problem from this. So this is like a one-slide summary of whatever I've explained till now. So I hope the potential takeaways is I would like to explain what is the general procedure for nonlinear FEM, how automation of finite element methods work, what is ASGen, what is ASFEM, and finally how to model contact between beams. So the future work is I'm trying to use WAM, which can be used for an anisotropic case. The additional complexity is instead of considering isotropic, we use anisotropic, and then this creates a complication, little more complications in the formulation. So I'm trying to model. Thank you.
So you are using. So thanks for the presentation. So first is a question and then a curiosity. So model contact is always difficult. So I see all the details, but it's difficult, I know. So what do you have in mind? Why you want to model the contact? What you want to do with this beam?
So the current tool that we have is most popular one is this. There is the tool's name is this finite element solver for textile composites. But that tool uses a beam element which doesn't consider cross-sectional warping. So the use of WAM is that we can consider cross-sectional warping, and we are hoping that this will lead to a more realistic a tool where we can represent how the textile composite.
But you want to model the contact between the
beams, considering WAM as the.
So between two beams?
Two beams.
For deformation, which type of application you are?
Currently, I'm focusing on static applications. But so the usual thing which happens is that
looking at physical problems, which are like examples of beams in contact.
So the woven composite case, this is the usual structure. So they have this. This is replaced as a beam, and then this is replaced as a beam. Now they apply biaxial load on both sides, and then try to see what is happening and validate.
Okay, so both of the yarn
you
present as a beam. Okay, so then it's becoming really detailed. Yeah.
So the reason why this woven is preferred is because the braided thing has the beams wrap around each other, and the contact modeling is very difficult there. So woven is, and usually woven composites have superior properties, I think, based on applications also. This was the one that started the textile composite application. So that's why people use it.
And then I have a curiosity. So it's a lot of work for master cases. How long is the master case here?
No, it's 2.5 years, but it's MTech research. So yeah.
So the normal time is
we have two types of masters. One is masters by course.
Yes.
So that gets over in 2 years, exactly, for all students. Whereas this is MTech by research, where there's less number of courses that they credit, and they focus more on the research problem that they do.
So they start the cases already the beginning of
Right.
And then if you do a master test, like say, so when it will finish in 2.5 years, or 3 years, 4 years?
Three is the maximum people take usually, but 2.5 to 3 years.
And then usually you do this type of master with research because you want to do a PhD, or because
yes, that's the primary.
So there's a possibility you can convert the research into a PhD by extending the problem. So they continue on the same research,
And then they count maybe not 4.5 years, but then.